Hello everyone. This video serves as an introduction to a new subject that we will be exploring in this video playlist. Process dynamics and controls. In order to give you a brief introduction and the motivation to study this subject, we'll start off by a very commonly encountered chemical engineering problem. Let's say we have a continuously stirred tank reactor in which we have a reaction A going to B, and the reaction is exothermic. We have a raw material feed rich in A, and we have a product feed rich in B. So these are the valves that control the feed and product flow rates. Okay, and the level of the CSTR is some level is represented something like that. Okay, and in order to cool this reactor, we have immersed coils through which we are flowing cooling water. So the cooling water is going to remove the energy released from the exothermic reaction and keep the vessel operating at a desirable temperature. Now, okay, let's say we want to maintain the contents of this vessel at a certain set temperature. Okay, now the set temperature could depend on the equilibrium of the reaction. It could also depend on the safety. The utmost importance is going to be safety, and the next factors are going to be economic considerations, whether you can achieve a good yield and kinetics at that temperature. All right, so the temperature of this vessel is what we want to control. How do we go about doing this? Okay, first we need to measure. We need some mechanism of measuring the temperature inside this vessel, and that can be done very easily by using I'm gonna use a thermocouple that's immersed inside the vessel that gives a reading of the temperature inside. TT stands for temperature transmitter. Okay, good. Now we have a measurement. Now this measurement needs to be compared. It needs to be compared with our desired value, our set temperature. T is our actual temperature of the process, and T set is the process where we want to maintain it. Okay, now the addition subtraction of these two values is going to generate an error term. And this error term is going to be operated on by a controller. A controller is basically going to be a computer that is going to take an action based on the value of error. Now, the most common action that the controller will take in most schemes, let's use a different color scheme. I'm going to use gray. The controller will manipulate the position of the valve. Okay, so we measure the temperature, we compare it with our set value and take an action on the error, and then we adjust the position of the valve. So if the temperature goes up, let's say you want to open the valve, and if the temperature is getting too low, you want to close the valve so that you are within the desired range of operability. What we've just done here is a very simplest is one of the most simple examples of feedback control. Feedback control can be summarized in three letters: M, D, A. Measure, decision, action. In our problem, we measured the temperature. Then the controller took the decision based on the error value, and our action was the position of valve. Now this is just a rough conception of what is actually being measured, the decision tree and the action. As we dive deeper into the entire structure of feedback control, we will revise and further come up with more sophisticated definitions of these terms. Now, before you can actually implement control, before implementing control for any process, whether it's a CSTR, a heat exchanger, a distillation tower, anything, before you can actually come up with a good control strategy, what you need is a dynamic model of the process. In order to be a good controls engineer, you need to know as much about the process as you can. The better your data and the better your model for the process, the better you'll be able to control it. How do we come up with these models? We're going to be doing everything that we've been doing so far. Mass balance, energy balance. Now the caveat with these two is going to be that so far, up till your education in the chemical engineering curriculum, you've been used to writing steady state mass balances and steady state energy balances. We're going to switch that now. In order to have a dynamic model, you need unsteady mass and energy balances. So these two are going to be your bread and butter, your first principles that will be applied to virtually every problem, every process that you're trying to model in chemical engineering. You'll hardly there is virtually no process that for which you wouldn't need to write some sort of mass balance or some energy balance. In addition to that, we will be using our equations from thermodynamics, such as in this case we will need to know how exothermic our reaction is to implement a good control strategy. We will also need to know the kinetics of our reaction, how the temperature affects our reaction rate, and we'll also need to know the transport phenomena. In this case, for example, we will need to know the heat transfer coefficient and the area of the coils associated with the cooling water to achieve a good model. So we're going to be spending a good deal of time on learning how to come up with dynamic models of our processes. Once we have a good dynamic model, coming up with a control strategy is very easy.